Hello, AP Chem students, and welcome to topic 5.9, the pre-equilibrium approximation. So the learning objective for today is 5.9.a, identify the rate law for a mechanism for a reaction from a mechanism in which the first step is not rate limiting. So in topic 5.8, we looked at writing the rate law from a mechanism in which the first step is rate limiting. So the first step was the slow step. In this situation, we use the concept of something called fast equilibrium when that's the first step. So sometimes you'll see this label a fast equilibrium. You can also see that written as a double-headed arrow that looks like this with the word fast beside the step. So in equilibrium, the system has reached a balance where your concentration of your reactants and your products have stopped changing and the reaction proceeds in both the forward and reverse directions. And so if that is happening fast, then that means the two species are nearly interchangeable with each other, because when you form products, they turn around and form reactants, and then those reactants turn around and form products. So they're constantly going back and forth. So why is this special in mechanisms? It means that we can exchange the reactants for the products and vice versa. So this method of substituting uses that pre-equilibrium approximation, which says that the fast equilibrium step is assumed to have reached equilibrium before the subsequent slow step. This allows you to treat the intermediates as if they immediately convert to reactants in the first step, allowing your fast equilibrium reactants to be in the rate law instead of the intermediates from the fast equilibrium. And that's useful because if we can, we would like to not have an intermediate in the rate law. So sometimes you do have an intermediate in the rate law, but ideally we would not. So an example of this is shown below. So here's your overall reaction. So we've got 2NO plus Br2 yields 2NOBr. So that's our overall reaction. And here is step 1. You can see we have that fast equilibrium. And here is step 2. So first of all, does this mechanism match the stoichiometry? And yes, it does, because we've got one NO as a reactant in step 1, and we've got another NO as a reactant in step 2. So that adds up to Br2NO. We have Br2 as a reactant in step 1. And then we've got this 2NOBr, and we see that as your product. So that means that we have an intermediate. So we need to have this NOBr2. That's a product of the fast equilibrium, and then it's a reactant in slow 2. So there's your intermediate. So the slow step is what we normally use to write the rate law. But if we did that, the rate law from that slow step would include an intermediate because it would have that NO there, and then it would have the NOBr2. And so ideally, we'd like to not have the intermediate as part of the rate law. So, but that's okay, because in this situation, what we can do is we can use the fast equilibrium to substitute. So what you do is you substitute the reactants that are in fast equilibrium for that product in for your NOBr. So you take the reactants, you substitute it in for the products. And so when we do that, we get that your rate is equal to KNO, so this part stays, and then your NOBr2 becomes another NO and then Br2. And so then we can combine those together for a final rate law of rate is equal to K NO squared times concentration of Br2. That's it. That's all you do. So you just use the fast equilibrium step to substitute for the slow step. If any of you have ever done proofs in geometry, this reminds me a lot of this whole idea of like the transitive property of equality. So if you have A is equal to B and B is equal to C, then A is equal to C. It kind of feels like that kind of substitution that we used to do then. I know proofs are not always taught much anymore, but this has that kind of feel to me. So I always kind of like to mention that, just in case that might make it feel familiar to you too. So what should you be able to do with this? Use fast equilibrium expressions to substitute for species and rate laws so that a mechanism can be shown to match an overall reaction description. That is it, and I will see you soon for topic 5.10.